Thanks for coming back. This topic, or this area, is a major area of research that I'm involved in and continuing to be involved in, and it's producing some exciting results. And it's ongoing. I have a colleague, Mark Armitage in Los Angeles, who helps me with this work, and together I collect samples and he helps process them, and together we're producing some exciting results here. Most granites contain the black flaky mineral called biotite. It's a mica. As I said on Tuesday night, there are two micas, a white mica and a black mica. Some granites have both. And as you'll find out later this evening, biotite is also common in metamorphic rocks. That is, former sedimentary rocks and granites that have been affected by heat and pressure. And until I started doing this work, there was only one report of a radiohalo in a metamorphic rock, but we've completely overturned that now, and more has been found. So in these biotite flakes, we have embedded zircon crystals. Zircon crystallises early in the cooling history of a granite, and I'll show you a diagram about that a little later on. And so the biotite crystal grows around it, and so the zircon crystal is embedded inside the black mica mineral. And these zircon crystals contain uranium atoms. As I said on Tuesday night, zirconium and uranium have similar sized atoms, and they have the same atomic valency, +4. And so uranium substitutes for zirconium in the zirconium silicate lattice. And those uranium atoms, of course, are unstable. They radioactively decay, and each uranium atom at each step of the decay process shoots out an alpha particle, which consists of 2 neutrons and 2 protons. In other words, it's reducing the size of its nucleus so it can become more stable. Now, there are a total of 8 alpha decay steps as the uranium atom is transformed into stable lead. And I'm going to show you again the list of those decay steps in a moment. But there are 8 steps where this alpha decay process occurs. And so the uranium atom spits out an alpha particle to become an unstable daughter atom. That one becomes spits out another alpha particle to become another unstable daughter atom. The nucleus is still unstable, even though it's lost an alpha particle. And so there are 6 more steps after that until you get to the stable lead atom. Now, when the zircon crystal is large, and they're often large and quite visible under a microscope, the alpha particles don't escape from the zircon crystal. And in fact, they capture stray electrons and become helium atoms. And we talked about helium in zircon on Tuesday night. It's a direct outcome of the alpha particle, which has 2 neutrons and 2 protons. All it has to do is collect 2 electrons, and it becomes a helium atom. And so for every uranium atom that decays, you actually produce how many? 8 helium atoms from every one of those steps, those 8 steps where an alpha particle is produced. However, in the biotite crystals, the zircon crystals embedded in them are usually very tiny. 1 micron is less than the thickness of a human hair, so it's quite small, but it's visible under a microscope. And these alpha particles shoot out like little bullets from the zircon crystal into the surrounding biotite. And as I said on Tuesday night, it's like taking a gun and firing a bullet through a plasterboard. It leaves a trail of damage, and that trail of damage discolours the biotite crystal. And so this is called, this discolouring, as you can see in this photograph. You can see the central zircon crystal there, and you can see all the damage, the discoloration, This outer ring is the most energetic alpha particle that makes it out that distance. This area in here is all dark. You can't distinguish the other rings because this has had so much radioactive decay. It's blurred all the damage together. And so we call, of course, this is happening in 3 dimensions. So in reality, it's a sphere of damage. But when we examine the rock, the biotite is flakes that are stacked up on top of one another like a book, of the pages of a book. And so when we collect the samples and separate the biotite crystals, we pull the leaves apart and so we're only looking on the page of the book. So you have to imagine that there's all these sections through this sphere. And you have to get through the central one, the central page that has the zircon crystal on it to identify the halo. Otherwise, if you miss that, you could be thinking it's a smaller halo and misidentify it. I can see some heads nodding, so that's a good sign. Okay. As I said on Tuesday night, each of these bullets travel different distances because the parent-daughter, the daughter then becomes a parent that spits out a daughter, and they each eject alpha particles at different energies for each step in this process. And so you can see in this diagram the list of the atoms that spit out the alpha particles, and you can see the energies. The most energetic one is the polonium-214, and so that's that outer ring there, because the bullet has travelled the furthest distance. It's like having different guns that will fire the bullets different distances. Now, because most of the damage is done when the bullet comes to rest, normally you expect to see 8 rings, as in this photograph here. And that's the giveaway. You can count those rings and you can measure the diameter of those rings, or the radii of those rings, and you can work out which ring corresponds to which element because of the different energies involved. And so you can easily identify that the most energetic ring, or the one that has the most energy, the bullet that has the most energy is polonium-214, and so that will be the outer ring, and so on. Now, of course, the pioneer in this work was Dr. Robert Gentry, but before him, they were studied, particularly in the 1930s in Canada. Henderson did some work on these halos, but never fully comprehended their significance or what they were. It has been determined that to fully form a dark uranium radial halo like the one that you see there on the screen requires 500 million to 1 billion alpha particles. So you have to have that many bullets being shot out into the biotite crystal around to produce enough darkened, damaged areas and those rings for it to be visible under a microscope. So when you see one that's blurred, the rings are blurred, you know you've had even more alpha particles than that. And 500 million to 1 billion alpha particles is equivalent to 100 million years worth of radioactive decay at the rate we measure today. Now, please don't misunderstand me on this point. I'm not saying the millions of years happened or existed. All I'm saying is that if the decay was slow like it is today, then to produce 500 million to 1 billion alpha particles would take 100 million years. That's at the slow rate we measure today. So that tells us that when we see a halo in a biotite crystal in a granite, this is physical evidence, literal, observable physical evidence that radioactivity has really occurred. And a lot of radioactivity. In this instance, with the photograph of this halo, 100 million years worth as measured at today's rate. And we have found in this research that granites around the world contain these dark uranium radiohalos. As I said on Tuesday night, I've had samples now from 5 continents. And whether it's in the Grand Canyon, or it's in southern Australia, or in southeastern Australia, in England, or here in the United States, we find these dark uranium radiohalos. So around the world, we find granites that contain observable physical evidence of abundant nuclear decay. However, in many granites, we find in the same biotite flakes as the dark uranium radiohalos, and the one here you see on the left on your screen is a dark uranium radiohalo. Again, you see the rings are blurred, which means there's been in excess of 100 million years. There have been so many alpha particles that it's blurred those rings. Everything's become dark. But alongside that, in fact, almost superimposed on it, is a smaller halo, also very dark, but it only has one ring. It's much smaller. And because of its radius, or diameter, whichever way you want to measure it, we can actually work out what element was responsible for producing that radiohalo, but more of that in a moment. And in some granites, we find not only the dark uranium radiohalos, but two-ring radiohalos. This one here, you can see the dark outer ring, the light outer ring, and the dark inner ring. And in some uranium, some biotite flakes, in some granites, we find all of these together, like the three-ringed radiohalos. And it's very hard to see but at this distance, but there are two rings in there. There are definitely three rings. Now, as I said, we can measure them and we can work out what elements were responsible for producing these radiohalos. Now, why do I say that? Well, if there's a zircon crystal in there that has uranium, we know it produces all 8 rings. So it's the element uranium in the centre, or what we call the radio centre, or the radioactive centre, that produces these rings. So when we've got a 1-ring, or a 2-ring, or a 3-ring halo, it must be an element other than uranium that's in that radio centre, that radioactive centre. Because if uranium was there, it would produce instead a uranium radiohalo. So what element is responsible? Well, it happens to correspond to the one element, but 3 isotopes of that element, polonium. Discovered by Marie Curie and named after her native Poland. It's a rare metal, and we can see it's the last 3 steps in the uranium decay chain. Now, these polonium radiohalos, because we call it a polonium radiohalo because it's parented by polonium. We call a uranium radiohalo a uranium radiohalo because it's parented by uranium. Now, these polonium radiohalos, again, are found in many granites around the world. Again, whether it's in Arizona, near the Grand Canyon, or in southern Australia, in England, or here in the United States. These granites all around the world contain these polonium radiohalos. But in 1989, at a famous trial, the Creation Evolution Arkansas trial in 1989, Robert Gentry presented this information on the witness stand. And when the ACLU put up its response, the man on the witness stand was G. Brent Dalrymple, who was then the Deputy Director of the US Geological Survey and is currently at the University of California, Berkeley, in their geochronology laboratory. And in response to Robert Gentry's evidence, he simply said that these polonium radiohalos were a very tiny mystery, period. In other words, he didn't offer an explanation. He didn't have one. He didn't have one. So why are they a very tiny mystery? Well, here we're going to add some more details that I didn't add on, or didn't say much about on Tuesday night. You see, these 3 unstable polonium isotopes only have fleeting existences. They decay very rapidly. Polonium-218 has a half-life of 3.1 minutes. Polonium-214, a half-life of 164 microseconds. If you blink, it's gone. And polonium-210, 138 days. Now, as some of you already know, it only takes 10 half-lives before you've put virtually, it's all decayed away. So for 10 half-lives of polonium-218, that's only 30 minutes. For polonium-214, that's 16.4 microseconds, and it's all gone. So how do you form a halo in that time frame? That was the very tiny mystery. What was Robert Gentry's solution? Obviously, these polonium radios had to form very rapidly. So what was Robert Gentry's solution? He claimed, and you'll read about this in his book, God's Fingerprint, that the polonium radio halos were created. They must be God's fingerprints of creation. He concluded that the polonium had to be created in place in the granite separate from the uranium, because there was no known process that could separate or migrate the polonium from the uranium to produce these halos. And so all granites, he said, had to be created, rocks, no matter where you found them. You see, you need a concentration, a total concentration eventually of 50% of polonium to get that number of alpha decays. Now, he said it all had to be at once, but I believe he's wrong there, and I'll show you why in a moment. He concluded 50% concentration had to be there, bang, ex nihilo, when God created. Now, the problem is, of course, for polonium-214, you'd have to get that concentration within a millisecond or two, a blink. So indeed, seems to be an almost insolvable dilemma. But here's the question. Why would God create the polonium radio halos and then allow the uranium halos to subsequently form alongside them over millions of years in the same biotite flakes? That's one problem. The other problem is some of these granites can be shown to have formed during the flood, the year of the flood. I'm going to show you one of those tonight, the one that I referred to on Tuesday night, where you can walk from fossil-bearing sedimentary rocks a mile to where the heat and pressure began to metamorphose the rock, another mile to where the rock was so metamorphosed that it started to melt and form a granite. In other words, the granite was derived by heat and pressure melting a fossiliferous sedimentary rock. Therefore, the granite could not be a created rock. It was formed during the flood. So all you have to do is to produce examples like that, and that falsifies Robert Gentry's model for God having created all the granites. So does that mean we can just throw away the radio halos? Not at all. Not at all. They still have something to teach us. It's like any scientific endeavour. Someone puts up a scientific model, it hangs around for a few years until people find problems with it, and then they propose an alternative model. Now, someone might come up with a better model than the one I'm proposing in the next 30 years. Well, great. We're getting closer and closer to the truth. So it's not about, fighting over these issues. It's about doing better science to build better models so we understand God's world better. Because he's told us to use our minds to worship him and glorify him in exercising dominion over the world that he's given us. So we need a new model for the formation of these radio halos. So here's the clue. Since polonium is a rare element, where in the biotite flakes could the polonium have come from to form the radio halos? I mean, this was the key question that struck me, that gave me the answer. You see, you have to ask the right questions to get the answers. And that's what's happening in the evolutionary community. They're not asking the right questions. But when you ask the right questions, you'll say, now wait a minute, there is a source of polonium right there in the biotite. What is it? It's in the zircons. You've got, remember, you can see in these photographs that polonium and uranium radiohalos are side by side. Usually they're less than a millimetre apart. And sitting in the centre of the uranium radiohalo is a zircon crystal that's full of uranium. And that uranium decays to polonium. You've got a nearby source. So, next question. How do you get the polonium from the zircon crystal out in the biotite to produce the polonium radiohalo? That's the next difficult question to answer. But it does tell us if the source of the polonium for the polonium radiohalos was in the zircon crystals, that means the uranium and polonium radiohalos had to form at the same time. And that's a very important lesson that we concluded on Tuesday night. Why is that? Because that means to get enough polonium to produce a polonium radiohalo at the same time as a uranium radiohalo, you have to get 100 million years worth of uranium decay in just a matter of minutes at the same time to produce the polonium radiohalo. So, as I said on Tuesday night, it's evidence for accelerated nuclear decay during the flood when many of these granites were forming. So you have to have a mechanism to deliver enough polonium from the zircon crystal to a nearby location in the biotite crystal with enough alpha particles to form each dark polonium radiohalo before the polonium decays. And the answer is quite simple, as we'll come to in a moment. But what it means, as I just said, that at least 100 million years worth at today's rate of uranium decay has to occur within hours to days for these polonium radiohalos to form alongside and at the same time as the uranium radiohalos. So, at this stage we can conclude, before we progress to a solution here, the dark uranium radiohalos in many granites around the world are observable physical evidence that abundant nuclear decay has occurred during the flood and in Earth history at least 100 million years worth at today's rate. Now, when we get granites at different levels in the geologic record, you sum total that and you can realise that we're talking about hundreds of millions of years worth of decay during the flood, for example, which we concluded from other evidence, but of course at an accelerated rate, because coexisting uranium and polonium radiohalos must therefore, having formed at the same time, be observable physical evidence that this abundant nuclear decay had to have occurred at an accelerated rate. You might say to me, but if the uranium decay was accelerated, why wasn't the polonium decay accelerated? Or the carbon-14 accelerated? But were you listening to what I said on Tuesday night? What did we find? The slower the decay rate, the greater was the acceleration. That means the faster the decay rate, the less acceleration. Uranium has a half-life of 4.5 billion years. Polonium has a decay rate today of minutes, seconds, and days. So would polonium have been sped up? No, neither would the carbon-14. They would not have seen significant effects from this accelerated decay process. Okay, let's consider how these radiohalos might form. Let me propose a model, and then we're going to test that model. We're going to test that model, because that's what we do. We put up a scientific idea, and then we go out, collect samples, process those samples to test that idea. And if the testing confirms our idea, it gives us more confidence in that idea. Now, this is an end-on view. These are the biotite flakes stacked on top of one another. We're looking at the end of a book, and you can see all the pages stacked up there, okay? And in that slice, which is a vertical slice through the pages of the book, we can see there on the left the zircon crystal between two sheets of the biotite flakes. Okay, see, it's between two sheets. The zircon crystal is sitting there. And because we can see the polonium radiohalo in exactly the same microscope section, it means the centre of the polonium radiohalo is also between the same two biotite sheets as the zircon crystal. And that's important because these biotite sheets are easily pulled apart because the nuclear forces, the bonds between them, are weak. And that provides a conduit between those flakes. It's easy for fluids to travel through. Now, one of the things we know, before I make this point that you see there on the screen, many people don't realise that granite, when it is molten, you have a blob of molten rock called granite that's going to cool and crystallise. It can contain up to 24% of its volume as dissolved water. So that when the granite minerals crystallise, any water that doesn't get locked up in the crystals is free to move around in amongst the crystals after the granite has cooled. And in fact, what most people don't realise is that metals like copper also don't fit into the mineral lattices of the crystals, and the copper atoms are free to move around in the water, which is how we get the copper concentrated to form copper deposits in granites such we find throughout the Rockies and the Andes. Around Tucson, we've got these large open-cut copper pits, copper mines. It's all in granite, copper that's come as a result of hot fluids coming out of the granite. And that's the key. The hot fluids that are produced in the granite as it cools. They're available, therefore, to dissolve polonium and transport it through the sheets of the biotite flakes. One thing we know, however, which is a very important aspect of this research, is that the radiohalos can only exist when the rock is below 150 degrees C. That's 1.5 times the boiling point of water. You might say, but can water exist above 100 degrees? Absolutely. You have superheated steam. And water first appears in a granite magma at about 390 degrees C. Now, how do we know that the radiohalos can only exist below 150 degrees? Remember the drill hole I told you about on Tuesday night where they drilled at Los Alamos into that granite to test for geothermal energy? The granite from which the zircon crystals were taken by Russ Humphreys to examine the helium leakage rates? Well, remember the table that had the different temperatures as you went down the drill hole? If you study the radiohalos in that granite, they disappear at 150 degrees. Why is that the case? Well, remember what's happened. The bullets have been shot out into the surrounding biotite crystal. What they do is they damage the crystal structure of the biotite, push apart the layering and the way the atoms are bonded together. What happens when you heat something? The heat transfers energy to the atoms inside the material. So what happens, the heat transferred into the biotite crystals causes the crystals to vibrate more rapidly, and what happens at 150 degrees, there's enough energy, they lock back to their original position and eliminate, anneal or wipe out the damage. Okay? Now that's a clue that Robert Gentry didn't know about. And it's very strategically important because it has incredible implications, as you'll see in a moment. So, in this process, we've got the uranium radiohalos beginning to form around the zircon crystal. And as it starts out shooting the bullets, the uranium atoms start going through that decay chain and they start producing polonium. Now, polonium being and radon is the step before that. Radon, it goes down to radon and then to polonium. And that's significant. Why? Because radon is a gas. And radon is also chemically inert. It will not be inhibited in the chemical environment in the zircon. So it's free to leak out of the zircon crystal, just like the helium is free to leak out. So what will happen? If the radon leaks out to the surface of the zircon crystal and then decays to polonium, now the polonium is available to the hot waters flowing past between the sheets of the biotite flakes. And how do we know that water does that? Because biotite changes colour as a result of hot water flowing through it. It's altered to another mineral called chlorite, which is greenish, when most biotites aren't. And so the uranium decay supplies radon and polonium to the hydrothermal fluids. Now, interestingly, I discovered when I began to look into this research, I found a book from the 1960s which talked about the chemical properties of polonium. And what did I discover? It loves chlorine. Guess what's the highest component in, well, common salt is chlorine. What's the commonest component in salty waters? Chlorine. What's the common component in hot fluids from volcanic rocks? Chlorine. So you've got the chlorine flowing past the zircon crystals, and the polonium just says, I love you, and off it goes. It behaves the same way as the element lead. And so it can easily bond with chlorine atoms attracted by the chlorine and flows out in the fluids. And so the model says that the hot water flowing through will take the radon and polonium to a nearby site. And interestingly, between these sheets of biotite, okay, the sheets are made up of a ring structure. The strength of the crystal is in this direction. Between the crystal is weak, which is why it peels apart. These sheets are held together by various atoms, including hydroxide components and also metals. In fact, copper sometimes links these two chains. And therefore, you only need something like sulfur or chlorine in that location to pull the polonium out of solution. Interesting, in the last 2 weeks, we've been actually extracting the centres of polonium radiohalos to study them and chemically analyse them. Often, there's nothing there. It was probably originally a fluid bubble that concentrated the polonium in hot water with chlorine. And if there was chlorine there, it would precipitate as salt. And guess what? You know, while I was in the Grand Canyon last week, they started this analytical work. I haven't read all the emails yet, but I noticed they're talking about salt. So again, it's a verification of this model. And so once the polonium is carried, either the radon is transported, and radon does dissolve in hydrothermal fluids. I also found that out. So the fluids can carry both radon and polonium. And that's important because if you're going to get a polonium-218 or polonium-214 halo, it probably is going to be radon that does the transport. Because once it turns to polonium, the polonium is gone in no time at all. So both of those elements have to be able to be transported by hydrothermal fluids, and experimental evidence confirms that. So once the polonium is concentrated, and here's the key. Remember I said that Robert Gentry said all of the polonium had to be there all at once? Well, why? And that creates a problem. Now we have a solution. Why? Because once the polonium arrives in the radio centre, what is it going to do? Decay. But it's going to leave behind the chemical conditions that are able to grab the next polonium polonium atom that's flowing in the water. And so instead of having the 50% all there at once, you can build it up progressively through time as the water flows along and the atoms decay. And so you get a progressive build-up, more atoms come in, and that's what I'm depicting here until the polonium atom forms. So you've got, say, a sulfur atom there. It attracts the polonium because polonium sulfide has been found in volcanic fluids adjacent to volcanoes, for example, in Italy, and it gives off the alpha particles. More polonium flows along to replace the polonium that's just decayed, and so eventually you form the polonium radiohalo. So, what is the evidence for this rapid hydrothermal fluid transport model? Well, the short half-lives certainly indicate it has to be a rapid process. The short distances are fine, less than a millimetre. We often find empty bubbles that probably were filled with fluids, and now we're finding evidence of salt crystals that are left over from those fluids. And interestingly, and this is the crunch that we're going to test, the greater number of polonium radiohalos therefore implies there were greater volumes of hydrothermal fluids in those granites. Here's a way that we can test this idea. If it is the fluids, the more polonium, the more halos. So there are some restrictions, as I said, as I'm going to indicate, in implications. As we said, fully formed uranium radiohalos require at least 100 million years worth of decay. Only that much decay will supply the polonium concentrations needed for the polonium radiohalos. Again, radon has only a short half-life of 3.8 days, so the whole process has to be extremely rapid, which implies that the transport and the formation of the polonium radiohalos, the transport of the polonium and radon, and the formation of the polonium radiohalos had to occur within hours to days. Now that's going to be significant, as you'll see in a moment, because I'm going to apply this research. And as I've hammered time and time again, 100 million years of uranium decay had to have occurred concurrently as the uranium radiohalos formed and the polonium radiohalos formed, I should say. Thus, uranium-238 decay had to be grossly accelerated. But here's the crunch. The zircons were decaying as soon as the granite magma started to cool, which means polonium and radon were being formed from the very early stages of the cooling of the granite, from 650 to 730 degrees, but the halos themselves can't form in the biotite crystals until they're as cool as 150 degrees. So the polonium and radon has got to survive long enough with a high enough concentration to be captured by the fluids and transported to form these radiohalos. So what does that mean? The granites had to cool within days. Now we're getting to the crux of the issue. Because you see, how many times have we been told, for example, by Davis Young, Christian geologist at Calvin College, from his first book to his most recent book last year, that the granites have to take millions of years to cool, and so it can't have been a young Earth. Well, here we have in the radiohalos evidence that the granites had to have cooled within days, because otherwise the radiohalos, the polonium radiohalos, would not have formed. And this diagram has already appeared, published in our Answers Research Journal, in articles on the radiohalos. For example, earlier this year there was an article on the granites in Yosemite, which I'm going to refer to in a moment. But here we have the granite forming. The molten rock is pushed up and intrudes. It's at a temperature way up there. The zircon crystals are already forming in the granite. And then the other minerals crystallise, and they're all crystallised by 570 odd degrees. The first fluids are released below 400 degrees, but here, down here, it's 150 degrees only below that we can form the halos. This is the time temperature window. So with the zircon here, up here, the radon and polonium are going to start being produced very quickly, particularly if there's accelerated nuclear decay. Unless the granite cools fast enough, all that decay is going to have occurred and all the polonium and radon is going to have gone away. That rapid accelerated uranium decay is going to have occurred and there's going to be no polonium left to form the halos. Okay, let's test the model. And I heard about this area of the United States, not just because it has lovely rhododendrons, it has lots of good rocks. And I thought to myself, now wait a minute. if we can find a place where I can predict where there might have been more fluids, therefore there should be more polonium radial halos, this would be an interesting place. Why? Well, here in the Great Smoky Mountains, east of Gatlinburg, there are metamorphosed sandstones. Now, sandstones often contain zircon crystals. In fact, that's the major source of zircon for zirconium metal. And in Australia, we mine the beach sands for zircons to extract zirconium. Okay, and when the rock metamorphosed, what happened? Well, some of the clay within the sandstone produced biotite. And also the process involved hot water. So here we have the three ingredients: a zircon to supply the uranium, biotite to be the repository for the polonium, and hot water to move it. Now, when you study the area, most people don't realise that you go in a metamorphic area, you can actually see different zones through the rocks where the metamorphism has been higher temperature and pressure. You get different minerals produced by higher temperatures and higher pressures. And the boundaries between these zones are where a new mineral appears. So, for example, if we go from Gatlinburg along the highway, we cross the garnet line. That's where garnets start appearing in these metamorphosed sandstones. We go a little bit further and we come to the staurolite line, where staurolite has formed in the sandstones, which is at a higher temperature and pressure. And we go a little bit further and we're almost into North Carolina, and we get the kyanite zone, or the kyanite line, where kyanite starts appearing. Now, if you've never heard those minerals before, don't worry. Go home and look up a mineralogy textbook. But here's the point. First of all, there we are sampling these sandstone. I mean, it's a lot of fun doing geology. You drive along the highway, pull up by a road cut and knock off. I did that once in Kingman, Arizona. A driver went past, he must have called the local police. They were around in a flash to see what we were doing, destroying the local environment. But here's what a metamorphosed sandstone looks like under the microscope. And you can see all the pretty colours. Now, here's the interesting point. At that line in the rocks where the staurolite crystals first appeared, that indicates that there was a metamorphic reaction. A reaction where certain minerals reacted with one another to produce a new, different group of minerals that were better able to survive the higher temperatures and pressures. What was that reaction? 54 muscovite or white mica formulae plus 31 chlorite, the mineral chlorite, produces 54 biotite, 24 staurolite, 152 quartz, and 224 water. Hello. At this line, there's a lot of water. So I said before we collected the samples, I predict that we're going to find more polonium radiohalos right at that point. And so we collected the samples. What did we find? More polonium radiohalos at that point. Actually, you can read about that on the website homepage at the moment, where we're showcasing predictions made by creation scientists in their research, and this is one of them. So that strengthens our support for this hydrothermal fluid model. Well, the researchers branched out into studying metamorphic rocks because this verification came from metamorphic rocks. And so in southeastern Australia, I've mentioned to you before, we have this metamorphic complex. It's actually near our highest mountains in Australia. Yes, we do get mountains in Australia, just over 7,000 feet. If you've ever seen the movie The Man from Snowy River, this is the area. And it's a classic textbook example of zones of increasing metamorphism of shales and siltstones. All the textbooks illustrate this example. At the centre, the temperatures were so high that the rock started to melt and form a granite. And as I said earlier, you can literally walk over the outcrops from fossiliferous flood sediments across the zones of increasing metamorphism right into the centre, into the granite. Sorry about the scale, but it's the elongation that's the problem. But here you can see these zones, and in the centre on the township of Cooma is the granite. Here's some of the outcrops, just again in road cuts, which are the easiest place to get to the outcrops, and this is what these metamorphic rocks look like under the microscope. And even in a regular rock-thin section, you can start to see the radiohalos are there. Many of them. In fact, many times the metamorphic rocks have more radiohalos than in the granites. And polonium-210 radiohalos were found in these biotypes right throughout this metamorphic complex. But the polonium-214 and 218 and uranium radiohalos were only found in the highest metamorphic zones where the rock had melted and in the granite itself. The radiohalo numbers increased progressively with increasing metamorphism, but they dropped down in the zone where the rock had begun to melt. And that's an interesting clue. But increase again in the granite. This matches the volumes of hot water. Why? Because when the rock starts to melt, it actually absorbs water from the environment and takes it out. And then when the granite cools, it releases it again. So again, we're seeing exactly what we would predict. More and more water as you go through the metamorphic complex. Then the rock starts to melt and soaks up the water, so you can't get halos. And then it releases the water when it becomes granite, and you get the halos. And that's exactly what we found, the pattern in the rocks. Here's some of those halos. Here's the traverse along the roads where the samples were collected. And here's the pattern. This low spot here is where the metamorphic rocks were melting to start to form the granite. The fluids increased with metamorphism, but once the rock started to melt, the melt absorbed the water, so it took it out of circulation so it couldn't form so many halos. And then when it formed, it crystallised, it released it back again to form more radiohalos. Now, isn't that exciting? It really does work. Well, back with granites again for a moment. In the Lake District of England, I mentioned this earlier, there is the Shap granite. In fact, it's very famous. Many of the buildings in London are clad with granite from this area. And this is one of these granites, like the Cooma granite, that we just saw, that intrudes into marine fossil-bearing sedimentary layers and volcanic rocks that would have been produced during the flood. And in fact, the heat and the hydrothermal fluids produced by this granite as it crystallised produced a huge alteration zone around it. In fact, it's one of the largest known in the scientific literature. Compared to the scale of the granite, it's a huge area, as we'll see in a moment. Interestingly, this granite contains large pink feldspars. The pink mineral in granite is potassium feldspar, and it's very pretty when it's very large, and many granites are like that. And they indicate that there were huge volumes of hydrothermal fluids this granite crystallised because they were able to precipitate large crystals. Here's the area of England we're talking about. It's right up near the border with Scotland, not far from Hadrian's Wall. And here's the Shap granite right here in the middle of this sedimentary and volcanic terrain. And this is a close-up view of the granite. It's only a small body that outcrops, and this dotted line is the alteration halo around it. And you can see where I collected some of those samples. Here's the quarry, the older quarry, that has produced a lot of the ornamental rock for cladding of buildings in London, and some of the samples came from that quarry. Here we can see the large pink feldspars, and they make very beautiful polishing surfaces for ladies to have in their kitchens. And so if you have a granite in your kitchen bench, just remember it's radioactive. Just thought I'd give you some encouragement tonight. Whoa, we've lost our... Let me go back quickly. That's what the granite looks like under the microscope, some of these large crystals. In fact, can we see a zircon crystal? Yes, that's a zircon crystal up there. Some of them are quite large. Here's some of the halos, the uranium and polonium radiohalos found in these biotite flakes. And interestingly, similar large numbers of uranium polonium radiohalos were found in all samples. Neither the granite isn't primordial, it was formed during the flood, and therefore the polonium radiohalos aren't primordial. They were formed after the granite formed during the flood, or as the granite formed during the flood. Again, with this diagram to show that it had to be as the granite reached the bottom of its cooling curve, below 150 degrees. Now, interestingly, the large radiohalo numbers were the same at the granite's edge as in the centre, in the more inward a bit. This sample here is from this location. Here's the boundary of the granite, right where that tape is. The sample was just taken right beside that. And these heat effects, by the way, also confirms that the granite was formed during the flood. It wasn't intruded cold, as Robert Gentry suggested as his solution to this problem. He suggested that granites were created and then they were intruded cold during the flood. No, here's the heat effects as a result of molten intrusion. Let's go to the Yosemite National Park quickly. That area, of course, is almost exclusively granites. And in the centre of the park, in the most accessible areas, is a group of granite bodies called the Tuolumne Intrusive Suite. Some of you may have heard of the Tuolumne Meadows, the high country. Well, that's where the name comes from. And these granite bodies were sequentially intruded into one another, as we'll show in a moment. As they were intruded, there are no boundary heat alteration effects between the later and the earlier granites. That means they were all still warm as they were each one sequentially intruded, which gives us a clue that the sequential intrusion may have been fairly rapid. Here's the area of California that we're talking about, the Sierra Nevada, and this is the Yosemite area here. And this is a geological map of the core of the park, and I know the scale is hard for you to read, but if you want the full-scale version, go to the Answers Research Journal on our website. And this paper appeared earlier this year, so you can print it out, attach it to an email as a PDF file, and send it to anyone else you like. And the samples are shown there where they were obtained from and all the data. Of course, it's a beautiful area, no matter where you look, it's granite. That's the back of Half Dome, that's some of the falls from Glacier Point, and this is in the high country up towards Lake Tenaya. And here's some of the outcrops, again on the road cuts. And the granites are an interesting rock to study. In fact, when I did my bachelor's degree, it was a granite that I had to map the boundaries of. And interestingly, just in the last few years, I've gotten from my archives the samples I collected 30 years ago during my bachelor's degree work to actually look at for radiohalos. And there'll be a paper on that shortly because it's come up with some interesting results. Here's what these granites, different granites of the Tuolumne Intrusive Suite look like under the microscope. Now, the interesting thing is the number of the polonium radiohalos increase almost exponentially from very few in the first intruded body, which is called the granodiorite of Cunha Crest, to large numbers in the last two of these sequentially intruded granite bodies, the Cathedral Peak granite and the Johnson granite porphyry. So there's a difference in the radiohalo numbers depending when the granite was formed in this sequence. This correlates, interestingly, and this comes right out of the research done by our secular colleagues directly with the evidence for progressively increasing volumes of hydrothermal fluids in these granite bodies. So again, there's a correlation, more hydrothermal fluids, more polonium radiohalos. And that again verifies the predictions of the model, which increases our support for that model. Here's some of the radiohalos found in these biotite flakes, and another, see the difference in the coloration of the biotite reflecting the hydrothermal fluids. The Cathedral Peak granodiorite, the second last of these granite bodies, the evidence for the high volume of hydrothermal fluids is again these large pink feldspars. Really large pink feldspars, just as in the Shap granite in England, the Lake District of England. And this is the sequence of intrusion. First of all, the green body is the granodiorite of Cunha Crest, and it cools progressively inward. The red area is the area that's still cooling. And not long after it, you get the Half Dome granodiorite, named after Half Dome, which is made up of this rock called granodiorite. And you see some of it has already cooled, and it progressively cools inward. Before that's finished, you've got another body, another phase of the Half Dome granodiorite, and finally, you get intruded into that, the Cathedral Peak granodiorite, and the last little bit is called the Johnson Granite Porphyry. Now, the interesting thing is, there's so much evidence of hydrothermal fluid in the Johnson Granite Porphyry that the steam would have built up to such an extent that as that rock was cooling, it parented a volcanic eruption. And this comes straight out of one of the books that is available on the geology of the area. This is the present topography. If you add on the rocks that have been eroded away, there's evidence that this was the chamber beneath the volcano, which became so full of steam that it exploded to the surface. No wonder we find so many radiohalos in that last formed rock. And that's quite common. Most people don't realise that underneath Mount St Helens, there was a hot body of rock that built up with steam and so much pressure from that steam that it eventually popped the cork at the top, which was the eruption. And that's what happens. And so if you have a granite magma, it actually has more water, so you're more likely to get an explosive eruption, which is why everyone is saying there might yet be another explosive eruption in Yellowstone National Park. So each granite had a rapid cooling time for each granite body, but each granite body in this sequence was still warm when the later granites formed, but not warm enough to obliterate the radiohalos that were forming. And so the total sequence of these intrusions in this Tuolumne intrusive suite had to be intruded, crystallised and cooled within a few weeks. Interestingly, I'll just close this section. This comes out of the second rate book. This is the conventional age of the granites that I studied, and these are the numbers of halos. These are the flood granites. Look what happens. More radiohalos while you had a lot more water around during the flood. This one here is way off the scale. See, that's about 70. It had to be, if we projected that up, it'd be way up in the ceiling. Which granite did that come from? It came from a granite that has ore deposits associated with it. Cornwall in England contains huge numbers of polonium-uranium radiohalos. That granite also hosts veins of tin, uranium, copper, lead, zinc that formed in fractures as a result of hot water flowing through to deposit the metals. More water, more halos. So the huge number of halos reflect the large volumes of mineralising fluids. Similarly, in a granite I'm studying in Australia, in Eastern Australia, it has associated with it hydrothermal veins, hot water veins formed from hot water, tin and tungsten, large numbers of radiohalos. So this leads to the possibility that we could actually use radiohalos in granites and other rocks as a pathfinder to find new ore deposits. If we find more radiohalos, we're getting closer to an area where there was more water capable of producing ore deposits. Exciting possibility. Who said that creation research doesn't have practical applications? Don't worry, I'm not going to become a millionaire out of this overnight. So further sampling and investigation of granites that host these deposits is certainly planned to test this possibility. And polonium radiohalos are certainly associated with ore deposits that indicate large volumes of hydrothermal fluids flowed to produce these polonium radiohalos, Again, we're talking about ore deposits forming within days to weeks, otherwise the polonium would not have survived. See how we can see now that these processes didn't require millions of years, that they were catastrophic during the flood. Well, let's conclude. Radio halos provide evidence of hundreds of millions of years worth of nuclear decay accelerated from today's rates. This provides us with a new model for the rapid cooling of granites in 6 to 10 days. This is the concurrent formation of uranium polonium radiohalos. The radiohalos provide a new model for the rapid formation and cooling of metamorphic rocks within days to weeks. A potential model for the rapid formation of hydrothermal ore deposits in only days to weeks. Of course, these timescales and processes for these processes would thus be consistent with the biblical year-long flood event. And of course, if a decay rate was accelerated, then the radioactive methods for dating rocks are thus unreliable and require a new model to account for much decay at accelerated rates within the scriptural framework of Earth history only of 6,000 years.